Welcome everyone to the GEOTOP-A seminar this week. So it's a pleasure to welcome Pablo Suárez Serrato from the Institute of Mathematics at UNAM, the National University in Mexico. And so he will talk about topics in geometric learning. So welcome, Pablo.
Thank you very much. Thank you, Fernando. And thank you to the organizers for this kind invitation. I'm very happy to present my work here. And I'm going to be talking about several collaborations that we've been developing in my lab and with my students and collaborators over the last few years. And before that, I want to give a brief overview of the development first in breakthroughs in artificial intelligence to highlight the fact that good ideas come from development of algorithms, but it's not until we have very good and very broad data sets that it's possible to have an actual AI breakthrough. So as you can see in these historical examples of artificial intelligence tasks like speech, playing chess, translation, being able to win at Jeopardy, classifying objects with computer vision, or playing games in Atari, we first had these very good ideas for the algorithms, but then there was a long time that had to take place before the actual breakthroughs happened. And it wasn't really until we had very good databases that the breakthroughs could happen. So I'm going to first begin by reminding everyone really about the history of the development of this area and to emphasize the fact that it's very important to have very good databases, because otherwise it's not really possible to perform these tasks at scale and then therefore to get breakthroughs. Just continuing with a very brief overview, in the late 1960s, there were developments in neuroscience to understand the visual cortex. And kind of parallel to that, there were proposals to realize that using electronics and using neural networks with the perceptron. And theoretically, the backpropagation mechanism was proposed in 1982, and then in the late 1980s, the first conferences in artificial intelligence started happening. And it wasn't until 1990s that we had these architectures like CNN, the convolutional neural networks, and LSTM, long short-term memory networks that were developed, which could only really be implemented with specific hardware, with graphical processing units. And then we have, after this, the appearance of a large database of images called ImageNet. And it wasn't until this happened that we were able to see this incredible explosion in breakthroughs and developments that were actually of commercial and industrial value. And this brief timeline ends in 2018 because the modern versions of these technologies use a thing that's called transformers. I'm going to leave that outside of kind of the scope of this talk because this is something that I think that is still in development. Now, let's review a little bit of the convolutional network architecture, which is already from 1998. If we have an image that's presented as a matrix with values that are entries on each pixel, then if we want to sweep a filter over it to, say, sharpen the image, blur it, or see whether there are horizontal or vertical lines, then this filter will be sweeping over and collecting information as it evaluates that smaller matrix along the image. And it'll populate this new convolved feature. And if we put these all together in layers, we will take one convolutional feature that will be evaluated there, and then on the following layer, it'll be evaluated there, and so on, until we get several layers that are distilling the information so that in the end, we can separate all of this into buckets that will hopefully, and in the end, in fact, separate our initial database into whatever we wanted to classify. This example takes the MNIST database of handwritten digits, and it separates it into 10 different classes over here. And this was the Linnet architecture from Jan LeCun in 1998. Moving on to more recent applications, we see, for example, that it's now possible to perform segmentation in analysis of medical images here on the left to analyze the growth of a brain tumor. And here we have the comparison between contours drawn expertly by people working in radiology and things that are found by machine learning systems. In the middle, there is a very interesting system developed by NVIDIA called Clara Holoscan, which they applied to COVID-19, where they were able to estimate the volumes and positions of COVID-19 affectation in the lungs. And for comparison, on the right, there's a similar system that figures out where the lesions for lung cancer might lie for emphysema. So here we can see that this is a technology that is very, very useful and that will certainly keep growing in its scope and applications, both in the scientific and engineering domains. Now, how can we as geometers, topologists, and statisticians and computer scientists contribute to this? Well, there's this growing field that I'm advocating for in this talk that I'd like to call applied geometry, which is similar to applied topology in that we could say that it encompasses a broad range of topics such as differential geometry, computational geometry, and geometric computing. But not only these, perhaps also algebraic geometry and other kinds of specific geometry like tropical geometry. And then computational geometry is really the development of the algorithms and data structures that allow us to perform these geometric computations. For example, here on the right, in my lab, we developed an algorithm to be able to approximate surfaces. So here we have an example of a thickened trefoil knot. And then at the beginning, we start with a ball, and our algorithm is able to progressively approximate the surface and create a triangulation that lies precisely on the boundary of the neighborhood of this trefoil. And in order to perform these things, we need to develop geometric computing. And this is an area that broadly covers all the computational methods for solving geometric problems. So whereas in pure geometry, we might be able to define a solution of a system of differential equations, like, for example, the Ricci flow, in geometric computing, we would actually need to be able to compute this explicitly using geometric methods that we can then implement inside the computer, so that there are other considerations like how a discrete approximation precisely follows the continuous version, and how stability problems in numerical analysis might create some problems or might actually be solved. As another application that we've been developing with this accelerated marching cubes method that we developed and that I briefly just showed here is looking at traces of neurons. So this is an image that comes from a file from a database that's called Neuromorpho that has many, many neurons. And the information there is slightly abstract. So it's actually a geometric problem to be able to reconstruct the 3D positions and thicknesses of these dendrites as they belong in the neuron. And there is a company that does this, and our software already is able to reconstruct these. And then this would then be able to be used in the future, collecting databases of all of these 3D scans of neurons to do 3D geometric computing. Similarly, this is useful for computing the reach or thickness of a neighborhood of some geometric object. For example, this is a graph that's embedded in R3, and the purple dots are lying within a neighborhood of a certain radius. So the area of geometric learning, we can think about it as learning on domains where the geometric information matter. And these typically will be manifolds and graphs. Now, here on the right, we have some examples of manifolds that you might be familiar with, just two-dimensional surfaces. They might be orientable or non-orientable. And on the bottom, we have an example of the Zachary Karate Club network, which is very well known in network science. So these are just examples to keep in mind of things that we're interested in when we think about geometric learning. And in general, we're thinking of graphs and manifolds. We could also be thinking of more abstract domains, for example, hypergraphs or simplicial complexes, or we could be thinking of more general objects than manifolds, such as Alexandrov spaces, orbifolds, RCD spaces, or just metric measure spaces with whatever structure you want. So it's possible to define this area of geometric learning just by defining your domain where you have a geometry of interest and then doing computations there. So when we're doing learning on manifolds as opposed to doing learning on Euclidean domains, we have very many differences. But in particular, when we have a flat structure of Euclidean space, we can translate along, say, these two axes, and that's one way to move around filters in convolutional neural networks. Whereas if we have a geometry in 3D space, it might not be possible to translate in a definite way, and then the filters will be deforming as we translate them. So we have to think about different ways of implementing these ideas. And I'm mentioning this now because I'll come back to this idea later. So for example, to get around these difficulties, one proposal that was, I think, very interesting was to use the eigenvectors and eigenfunctions of the Laplace-Beltrami operator, and these were called functional maps. And what we do here is we decompose a filter or a kernel that's based in like the belly button of this shape, and this is decomposed using the eigenfunctions here of the Laplace-Beltrami operator. So this is a way of using Fourier analysis to approximate a density function here and then make it computationally feasible. And just to highlight again that manifolds typically don't have a translation structure. So the naive version of extending a convolutional neural network from flat space to a manifold just simply does not work. So this is a big area of research where there have been very many proposals to define convolutions on manifolds and on graphs. So I don't know if anyone has a question up to now. Maybe you could raise a hand or. Okay, then I'll continue. So moving on, in the databases that exist currently for computer vision, they don't really take into account the genus distribution. So the homotopy type or the different changes in topology are not taken into account. So you might either be training on a single topological type, as we will see that is the case sometimes, or be training, as in this picture here, on different topological types. These are surfaces with different genus depending on the however many handles the back of these chairs have. And if this is not being taken into account as a tabulated piece of information within your database, then your architecture is going to be agnostic to it, or it might be figuring it out, but you don't have a way of tracking it. So I think this is an issue that as geometers and topologists we should address. And as ongoing work we've been developing in my applied geometry lab at UNAM, a surface database that has embedded and knotted surfaces. And these are some examples that I'm just showing visually here. And we have several hundreds of these already, but we're planning on having several thousands so that we can actually perform learning tasks that are more sensitive to the distribution of genus and that are able to learn things from different topological types of surfaces. Now, if we stop thinking about genus for a second and different changes in topology and think about one of the simplest manifolds that is not a flat plane, for example, the sphere. Already on the sphere, there have been very interesting developments on deep learning. These are images from Costas Danielidas' lab and are available on the GitHub repository where they host these spherical CNN implementations. So here you could see a spaceship and how it's being recorded in different filters in this spherical convolutional neural network. And then these filters are moving from one layer to the next. And then eventually we get the same thing as before with the MNIST and Linnet architecture, where we end up with a signature that represents our original space. And while it's fun to look at these spaceships and how they move around, this type of architecture and model has very many different applications. For example, to atmospheric sciences, looking at temperatures of the globe, or to different kinds of ecological considerations in terms for climate, for example. Although I'm also highlighting here the fact that in practice, we might not have a complete sampling that's IID with respect to the area measure of the sphere, because we don't have sensors that are well distributed across the entire globe. So this creates different kinds of statistical problems to consider also when dealing with manifolds and with dealing with real world data that has some sort of curved space shape like this one. Now, Another way in which manifolds appear naturally in the study of data is by what's known as the manifold hypothesis. And this posits the idea that data naturally lies on or maybe just near a manifold, so that if we take all of the collection of the data points and we find a neighborhood that contains them, that will be a smooth manifold of much lower dimension than the original data or than the original ambient space that contains the data. This has been considered very seriously by a number of people, both in physics and math, and it has also been proved experimentally using, for example, in this case, just images and seeing how they should lie on the neighborhood of a certain hypersurface of a manifold. And if we go outside of that manifold, they find that we just find noise. So what about the simplest kind of manifold, and how can we use that to approximate data? In a collaboration with my former PhD student, Eduardo Velazquez Richards, we used a mean curvature flow in a way in which I would think should be called applied geometric analysis, because we're using geometric analysis as an application. And we defined a geometric flow that finds a contour of a region and it automatically approximates it. And these GIFs here are showing you the progression of these curves, first as they approximate a convex shape, and also how they perform in a very simple non-convex shape. For a more realistic application, we also considered a database of melanoma lesions. So these are cancerous cells that are growing, and these are moles that start growing in whatever part of the body of a person. And as a clinician, the clinicians use how the contour stops being spherical as a measure to kind of understand how this is actually becoming cancerous. So this is a geometric characteristic, and this is something that we can precisely calculate using these methods. In order to perform this, well, we first have to show the existence of solutions to a system of PDEs, and then we approximate these numerically, and we give stability guarantees so that we know that these things are actually doing what we say that they're doing. And you can also look up the repo for this online, and you can check out the paper using this QR code if you're interested. Now, going back to the realm of graphs, I want to first explain that machine learning on graphs, this would be a subfield for graph structured data, where here we have nodes and vertices that are connected by edges. And in modeling things using graphs, we think of nodes as people, cities, or molecules, and then the edges might represent their interactions, such as friendships, road networks, or chemical bonds. And the goal of this area is to learn patterns and relationships in the graph structured data, and this might leverage its unique graph properties. Now, as I've mentioned before, traditional machine learning really operates on Euclidean data, or vectors that are in Rn. And this may not effectively capture the complex connections in graph structured data. So this is why this is an area that has been also growing very quickly and has found very many applications in social network analysis, in social media, and also in recommendation systems. For example, when you're choosing in your favorite streaming service a film or a series to watch, sometimes the recommendations are using these kinds of technologies. Also in fraud detection for banks or for financial institutions. Companies are using this already for drug discovery to find new medicines, and for many more that are just developing every day now. Now, what are the techniques in graph machine learning? One of them is to embed graphs in a Euclidean space and then work with technologies that we know work there. And then there are other ways of developing graph neural networks or graph convolutional networks and graph representation learning or creating clustering algorithms. So I want to focus on the first one and first kind of explain a little bit more that in these methods, we map the nodes or the complete graphs to a dense vector representation in some lower dimensional space in a way that we hope will preserve their structural properties. And then the way that we define the embedding will have a bearing on whether this actually preserves the properties or not. So in order to define one of these embeddings for you and explain how we use it to define a distance, I will go back to some ideas in algebraic topology. and specifically the object that's called the marked length spectrum. And this is a gadget that allows us to count lengths of minimal loops in free homotopy classes in a space. And a very interesting theorem of Constantin and Lafont, called the marked length spectrum rigidity theorem, tells us that the convex part of a one-dimensional metric space is determined by the marked length spectrum up to isometry. So if we're just thinking of metric spaces of one dimension up to isometry, then the marked length spectrum is a very good proxy for us to be able to know if they're the same or not. And the convex part here really just means that we're clipping away all the loose leaves or trees that are sticking out. All of these hairs that are sticking out, we're just shaving them off. And on the right, we have here a diagram explaining if we start with a graph that has a base point in different points, then we might have homotopy classes, and then they have a length spectrum because they're the lengths of these cycles. Or complete, this one's backtracking, so we go 1, 2, 3, 4, 5, but this one's not, so this is just 1, 2, 3. And then if we just think about these up to conjugacy, then we reduce the amount of classes that we're looking at. And then we want to just count the ones that are non-backtracking. So we're going to delete these 3 and just keep these 2. And then we're going to end up with what we called for this paper the relaxed length spectrum, which is not this completely, but it's an approximation that we will be able to compute. Because actually computing the whole marked length spectrum is a problem of exponential complexity. So it's not really accessible computationally, even though theoretically we might think about it and prove very interesting theorems. In practice, when we want to code things, we need things that are run in at most polynomial time and hopefully linearly so that they can scale. Now, how do we compute this non-backtracking matrix? This is going to tell us whether these cycles have an edge that goes back in on itself. And there's a very easy way to populate this non-backtracking matrix that I'm going to show you here visually. If we start with the red node and we go to the blue, and then from the blue we go to the yellow, then that one did not backtrack, so that has a 1. And that's the red goes to the blue and the blue goes to the yellow, so that has a 1. But if, in contrast, we went from the red to the blue, and then from the blue back to the red, that one went back on itself, it backtracked, so that has a 0. And then the same thing happens if we go red, blue, green, that one didn't backtrack, so that's a 1. So that's a way to populate this matrix. And we can also say, we can also use the delta Kronecker on the line graph to define this, looking at it as the adjacency matrix of the line graph. And the actual computation of the non-backtracking matrix is can be performed using this algorithm here, and it has a runtime complexity that is linear on the m and n entries that we have, and quadratic on the non-negative entries of the non-backtracking matrix. So if we have a sparse matrix, for example, a graph that's representing the triangulation of a manifold, because that's only connected to its neighbors, then this quadratic term is going to be very small. So the runtime complexity of this is going to be almost linear. If we, in contrast, have a very dense graph where every node is connected to each other, as in a complete graph, then this is going to be very big. So this is almost going to be quadratic. So those would be 2 extreme cases. Although you can see that in some cases of geometric interest, like triangulations, this runtime is going to be very good for us because it's going to be close to linear. Now, if we're only interested in the eigenvalues, and I'll explain why, then we could actually substitute this matrix by another one that's easier to compute, which is this B prime, which is constructed using the adjacency matrix, and then 1 minus the diagonal, and the diagonal, and then a 0. And it turns out, and these are some theorems in linear algebra, that B and B prime have the same eigenvalues that are different from plus or minus 1. So this is an interesting proposition and characteristic of these matrices that is useful for us computationally. So this is our algorithm to define a non-backtracking spectral distance, and this is a way of defining a distance between different networks. We first input the 2 graphs, and we define a distance, for example, Gromov-Hausdorff distance on the plane, or the Earth mover distance, which is the optimal transport distance between the multi-sets of points in the plane. And we choose a number of eigenvalues just to truncate it so that it doesn't run for too long, but it could just be the largest amount of eigenvalues of the two graphs. And then what we do is we do this procedure of shaving as a pre-computation step to make it easier to compute and faster to compute the eigenvalues. And then we take the largest eigenvalues of B prime corresponding to these two shaved matrices, and then we compute the distance that we defined in the beginning, and that's the distance between our two networks. Now, why is this an interesting distance to consider topologically? Because the trace of b to the n actually equals the number of non-backtracking cycles of length n in the graph. So this is giving us some sort of information that's in there in the homotopy classes of loops in the graph that have length n that is not available with other methods like topological data analysis that uses persistent homology that only tells you whether there exists a class. And here we're actually being a bit more precise in terms of the metric properties of loops. Now, notice that B is not symmetric, so its eigenvalues are complex. Probably should have mentioned this earlier, but this is why we have scatter plots on the complex plane. And here we have several examples of how this looks. For example, blogs of politics, political blogs and references between them, communication between pods of dolphins. This is the Karate Kid, a Sakura Karate Club graph that I showed at the beginning. And these are football teams and whether they exchange players within a season. These are the relationships between adjectives and nouns. And these are references between political books. And you can see that in all of these networks, we get a different distribution of points. And they're all kind of inside this radius. Now, what happens, for example, with generative families of graphs? For example, Erdos-Renyi, which is considered to be the random model of graphs, or Barabasi-Albert, which is used to model the connections within the World Wide Web, or the Watt-Strogaard's model, which is the small world model that also explains this idea that everyone in the world is connected with 6 degrees of separation. If we plot the eigenvalues of these graph models, then we see that we get different scatterings. And the Erdos-Renyi is the perfect circle, and there's a theorem that tells us that, but we don't really have clear theoretical results for any of the other ones, to be honest. So we can make experiments now, and then we can see how they compare. And I think this is very interesting because it allows us to visually verify or discard a hypothesis of whether a complex network that's modeling some sort of physical or social phenomenon adheres to one of these models or not. And in fact, these are the examples from real world data that I have here, the controls in patients. These were functional MRI scans of patients that were under coma as compared to patients that were just controls. And you can see how these brain scans, from which a graph is extracted in a statistically robust way, has a scatter plot here that is very similar. It's almost indistinguishable, the pink and the black. But at the same time, we see that it is different from all of the other models. So even just with this example, or counterexample even, we can see how these fMRI scans don't conform to any of these models exactly. So I think that's interesting in itself. And moreover, in our paper, we explain how this can be applied to understanding phenomena that's interesting in network science, like hubs, the existence of triangles, how this can be used for developing clustering methods, and as an application for anomaly detection. And this here can be considered as a graph embedding, but we also use this in combination with UMAP to give a manifold learning embedding into both R2 and R3. And these visualizations are useful for conveying information quickly and also for, as I said, exploration of data and verifying or discarding of hypotheses. So I don't know if anyone has a question up to now. I'm going to kind of switch topics next. Okay, great. I'm also happy to be contacted offline later or after the talk or by email if you want to chat about any of these things. So next I want to talk about an idea that in differential geometry was first introduced by John Nash well, in the 1950s, when he was able to show that manifolds, Riemannian manifolds, can be isometrically embedded in Euclidean space. So at first I started talking about how manifolds, don't have a Euclidean structure, and how this might create computational problems for us. So now what I want to highlight is the fact that we have a theoretical workaround for this, and it is constructing an isometric embedding. Other useful strategies for different kinds of embeddings realize manifolds in L2, for example, or they can use the heat kernel or eigenvalues of the Laplace-Beltrami operator. So these are slightly different techniques. And now we actually have certain implementations of code for these ideas that use the Laplace-Beltrami eigenvalues, or that can strengthen topological Whitney embeddings. So there's this kind of play between what we conceive theoretically and what we can realize in practice using code. And by now, there's been very many advances in this direction. If we just restrict ourselves to Nash embeddings, which are good because they preserve the isometry type, they have this characteristic that the ambient dimension that we need to use for the embedding grows quadratically with respect to the manifold's original dimension. And this can be slightly improved so that so we can get Lipschitz control on the distortion, because as we do the isometric embedding into Rn, there's a lot of distortion that happens. However, this is just to highlight the fact that if we have a manifold of very high dimension, then the embedding dimension is going to be a square of that. So this is relevant when we're thinking about all of the different coefficients that appear in convolutional neural networks, as I'll explain in a second. Okay, so in order to explain how I'm going to use this, I want to go over a notion that's called the reach of an embedding. Now, the reach of an embedding, it's kind of how thick we can make the image of the embedding before it touches itself. So this might be easier to first visualize here, where we're thinking about this dotted line called the medial axis. And then the reach can be thought of in a way as the largest ball that can be fit inside of this neighborhood of the embedding. And this is the greatest width of a tubular neighborhood, such that its boundary does not intersect itself. And here on the right, we have a couple of examples of, this is a machine part and the reach of an embedding of this CAD realization in 3D of it. And in this dragon, we can see the different colors of the reach of the embedding here. Okay, and in a database that's very well used and known in computer vision called FAUST, this database introduced 100 different images of people in poses, and it was fundamental in the development of different technologies in computer vision so that people could actually now use a database for training and develop different techniques for convolution and for learning in geometric domains. Now, while FAUST has been very important, and I think it's been fundamental, it is one of these databases that only has a single topological type, because these scans are all just homomorphic to two spheres. So in fact, whenever we train only on FAUST, we're only training on a single topological type, and that's just the sphere. So we kind of, as geometers and topologists, have to have this in mind and contribute to the community of statisticians and computer scientists by letting them know that while this is great, we still should have things that are more diverse topologically and that cover more topological cases. And what we've done here is visualize one of these FAUST images. So if you look at the hand over here, this is just the original file. And then this is an embedding of a neighborhood that goes beyond the reach. And here I'm illustrating how the reach is important geometrically, because if it goes beyond the reach, then the fingers are actually merging into what looks like a mitten. So it's losing its geometric information. In contrast here, I've done a zoom of this image where we created a neighborhood that just goes beyond the reach of the embedding, so that the thickened part here is just small enough that when we take this slab off, we can barely see it, but it's there. And that's actually going to be a neighborhood that's underneath the reach, so that it's just thickened enough that it still preserves all of its geometric properties. And now, using the reach, it's possible to define a global convolution operator for compact smooth N manifolds. now what we have to do is use an isometric embedding, and that can be done in 2Rn, but I guess for reasons of preserving the elegance of Fourier analysis, it's probably better to think about it as being embedded into an n-torus so that everything is well defined there. Now, how do we do this? Well, given two functions in M, we denote this tie convolution of f tie k applied to x as the integral of over the torus that we embedded in the ambient dimension n of k bar times f bar. And then this is going to be of the embedding that we're doing. So we've already embedded everything in there, and then these extensions are and the way that we extend this is what allows us to define this convolution. So how do we extend this using the reach? If we had a circle, then a neighborhood of the size of the reach would be this flan, where we have this bump function that can also be thought of as a flan function that's just thickening it up, and it's making it a little bit three-dimensional so that we can actually work on it in 3 dimensions. So how can we illustrate this? If we have here a 3-dimensional object and it's just lying in 3 dimensions, first we have to process it so that we can work with it on the computer. And then we thicken this up using a neighborhood of the reach. And then in here, I'm also showing kind of a voxelization so that we can more clearly visualize how one of these filters would now be sweeping not just in 2 dimensions, but in 3 dimensions so that it can go everywhere. And then that way we can get an analogy for the sweeping of filters in convolutional neural networks for images in dimension 2, but in higher dimensions. And in fact, there have already been a couple of voxel neural network architectures that use these ideas. So this is another good point to ask if anyone has any questions up to now. Okay, well, in that case, I'll continue with kind of the next topic, which we're really switching gears now, it seems, and we're going to talk about Poisson geometry. So this is a brand of geometry that was started by Simenon Poisson in 1809, and the idea was to introduce certain ways of understanding classical mechanics and understanding the motions of the planets. Now, this is by now an area that has grown very much, I would say, and has very many relationships to algebra, to different branches of geometry, not just to mechanics, but also to quantum mechanics. And I think that it describes dynamical phenomena that is interesting, and it also has very interesting geometric properties in its own right. Here we see, for example, how a vortex fluid flow would be flowing. And this is actually what happens when a gun is fired and you get a vortex of air forming kind of right around where the projectile is passing. And this has the understanding of vortex rings has very many applications in natural sciences, for example, in oceanography, meteorology, or plasma physics. So this is an area that's a powerful tool to understand different dynamics of vortex rings and classify them. So before I go deeper into Poisson geometry and what we've done computationally, I want to mention that first, this is a generalization of symplectic geometry. So in a symplectic manifold, we have a non-degenerate 2 form. For example, on a disk, we have dx dy, and on an orientable surface, the surface area forms are symplectic forms. Now, a Poisson bracket can be defined using just a product or an operation on the ring of smooth functions in a manifold with the following properties: that it's R-linear, antisymmetric, and it satisfies both the Jacobi identity and the Leibniz rule. Geometrically, a Poisson structure gives us a foliation by symplectic leaves that might be singular. For example, in R3, here we have two examples with the Lie Poisson structure of SO3, giving us these spherical concentric leaves that are singular at the origin, or the Lie Poisson structure of SL2 that gives us these conics that have the singular point at the origin. We can define a Hamiltonian vector field on a symplectic manifold implicitly using this equation, contracting the symplectic form. And in a Poisson manifold, we can define it using the Poisson bracket, using this other equation. And because of the properties of the Poisson bracket, we can also describe it like this, using this linear function between the cotangent and tangent bundle, where now the rank of the Poisson structure is going to be the rank of this linear map at the point x. And another motivation for studying Poisson geometry is a theorem that I showed with Luis Garcia Naranjo and Ramon Vera that tells us that all close to orientable smooth form manifolds admit rank 2 Poisson structures. So this builds upon the work of broken Lefschetz fibrations on smooth form manifolds. And what we do here is we adapt a Poisson structure to a broken Lefschetz fibration. And this also gives us another motivation to understand more of the properties of Poisson geometry so that we can understand smooth form manifolds, which is still an active area of research in math. So now what we did was with Miguel Ángel Evangelista Alvarado and José Ruiz Pantaleón was develop a toolkit of symbolic computation for Poisson geometry. And we implemented 19 algorithms that do all of these things. And they are freely available in this GitHub repo page. And we defined and designed them so that they could be used with PyTorch, TensorFlow, or NumPy. Or if you're working just in pure Poisson geometry, you can define a formula and then use it in LaTeX. And we have a counterpart that's a numerical version of this that actually includes optimizations of methods that involve matrices, and it also plugs into PyTorch, TensorFlow, or NumPy. Now, I'd like to highlight that these are kind of one-of-a-kind computational toolkits, and now I want to use the rest of my time to explain how we developed a machine learning, deep learning system to perform discovery and regression of symbolic Hamiltonian dynamics using these toolkits. And if you are very interested in learning more about these, here's a tutorial that we wrote, and it's available on GitHub, and you can run it on Colab, and it explains a bunch of different examples. So here you would have to, for example, define a bivector, and then define your favorite function to start with, and then it can compute the Hamiltonian vector field, for example, just automatically. And in this computation, it uses a certain syntax because it's a computer, but we can also get it to output the LaTeX code and display it as a formula. So that starting from a Poisson bivector and a function, it'll just compute automatically the symbolic version of the vector field, and then you can also use the numerical toolkit to evaluate it numerically, and then do numerical analysis or learning on this. So the systems that we defined, we call them symflux, as symbolic flux. And for example, consider a planar vector field. And this is an image that I took from the Jova hurricane, which was a Category 5 hurricane that was in this region of the Pacific about 6 months ago. Now, the question is, can we learn dynamics and express them symbolically? This is kind of what's motivating this direction. So we already saw that the definition of a Hamiltonian vector field comes out of this equation. And these are systems that satisfy these kinds of equalities, which are the Hamiltonian equalities. And such a triple M omega H is called a Hamiltonian system. And the Hamiltonization problem consists of finding a Hamiltonian system for some H that makes a given dynamical system or vector field or flow phi into a Hamiltonian flow. Now, this is also an active area of research, and we're kind of contributing this idea that using deep learning might help us, or it'll be interesting to see how it performs. Now, why would this be reasonable? Well, first of all, there's a theorem by Lee and then kind of expanded by Koenigs that tells us that a system of ODEs is reducible locally to a Hamiltonian system. And this is in a small enough neighborhood. So going back to this picture that we had of this hurricane, this might mean that in this little window here, we can describe this using an ODE. And the question then again becomes, can we learn these kinds of dynamics and express them symbolically? So as a proposal to approach this sort of problem, what we're doing is working on deep learning models that learn symbolic expressions of Hamiltonian vector fields on the standard symplectic plane. Now, this is the first case to consider, but as you can see and imagine, with our computational toolkits, we could work on any Poisson manifold or any symplectic manifold. And this is kind of, I think, what we'll be able to do in the future. But first, this as a test case, we want to develop these systems. In here, we're proposing a combination of CNN and LSTM submodels that take an image from a vector field, pass it through the CNN, and create a feature vector, as we showed in the examples before. And then this gets passed through a long short-term memory LSTM system to output a symbolic prediction. So this is a schematic of the architecture. And let me now briefly explain what an LSTM is. This was an architecture first developed to address the problem of vanishing gradients, and it was designed for time series for long-term dependencies. This is used in natural language processing, and it helps find symbolic expressions. And for example, in combination with CNNs, they're able to describe a scene. So if we feed it one of these systems that have CNN and LSTM architectures for scene description, if we give it this picture, it'll, for example, come out with something that says baby plays with dog, and it'll describe the scene very succinctly or very expressively, depending on how the architecture was defined. And these selectively forget or remember the information from previous time steps, and then making it more efficient and effective at handling data with complex temporal relationships. And we're not really using the temporal relationship aspect, but more the fact that it can recover a symbolic expression from an image. Now, let's go back to this history of breakthroughs. Remember that in order to have the breakthrough, we really needed the data set. And this is, in a way, what's been taking longer for us to develop these systems, because there aren't any data sets for doing mathematics or symbolic reasoning like this. So we had to develop our own. So we developed this system in 3 steps. First, we had to define a basis of functions. These BIs, the index here on the i's, are the exponents of the polynomial functions. So we defined a basis of polynomial functions, kind of taking inspiration from the Weierstrass theorem that tells us that any continuous function can be approximated arbitrarily well by a polynomial. And then we had to define a step, because we can't use real coefficients, because then our database would be infinite, and we need to have a finite dictionary of functions with respect to which we can describe the field that we're trying to understand and do inference. So this step means that we're dividing the interval -1, 1 in 3, 5, 7, or 9 different points. And as you can see, the growth of all of the possible functions that we can construct of polynomials of this degree with these different coefficients and steps grows very, very quickly. And in fact, for some experiments, we could not go beyond quadratic, and we're trying to run experiments using cubic. But already just the construction of a data set of this size would take 4 months. So this is where the limitations of computational power are very apparent when one tries to develop these sorts of methodologies. However, we were able to define a small enough or large enough database that we can work with, and then we evaluated on different meshes. We considered the canonical mesh, but also random point cloud meshes. Sorry, lattices. So this is the canonical rectangular lattice, and this is a random point cloud. And this is what the evaluation of a vector field would look there and there. And then we turn these images into these vector fields into images that are fed into the CNN using 3 different methods to augment the data. So these are 3 examples of just a single vector field, how it's processed to be inputted into the CNN. And these are some of the results that I want to present today. So we have 3 different models using 3 different convolutional neural network submodels that are VGG19, VGG16, and exception. And you could see something very interesting, that as we swap out the different CNN submodels, we get different accuracies, which are increasing. And this is our best accuracy at the moment, 89%. So here's an example where we have an image of a vector field with a Hamiltonian function h1, which is given by this polynomial here. And here's another one, h2, given by this polynomial here. So this is what these vector fields look like. And here on the right, we have the prediction given once we use these systems for what the polynomial should be. And you can see that the first one is not very good, but the last one actually hits it exactly on the nose. So that one's actually quite good. And obviously these are, you might say these are cherry-picked examples, but as you can, we also are showing you one where it actually gets better with the model. And in this one, another, I guess, also cherry-picked, but also to show the fact that even though it might get better, it might not find it completely. Like in this case, it doesn't get x squared minus y squared. It gets x times y minus y squared. So this isn't, it's learning something that's similar. And it might not get 100% accuracy, but it's kind of approximating it. And we're currently still training using UNAM's MISTLI supercomputer, which I'm highlighting here, using a 20 million image database. And this is larger than ImageNet. And in here, I think these have been very interesting and very exciting developments, but they've also showed us as a research group how it's going to be very hard to leverage the power of these technologies without having databases. So we kind of have to go back to the step zero of developing your own database, and then having enough computational power and storage space and RAM to use these databases. So this is, for example, not possible at the moment for us for anything in 3 dimensions, because we don't have machines that are large enough for the RAM needed for 3-dimensional databases. And for a database of this size, we would also need to take several months just to create it. So I think it's kind of opening the door to the possibility of performing this sort of deep learning on different sorts of dynamical and geometric objects. And finally, I would just like to say, going back to the computational toolkit, this toolkit was featured in the American Institute of Mathematics newsletter when it came out as one of its featured articles. It was also the reason that Miguel Ángel Evangelista won an AI prize from Afirme and UNAM last year. And this was included in the in a repository that's going to be kind of kept forever in GitHub. And it's also in one of the deep learning databases for learning code that's called the stack, if you're familiar with that. So this is already kind of going to be featured forever in several ways. But in a way, what we've been able to do, and what I've showed here, is just using one algorithm, which is the creation of Hamiltonian vector fields. And we have 19 different ones. So I just want to finish with an invitation by saying, if you're interested in this, there's a ton of different things that you can play with here for doing things with Lie groups, or just verifying that things are Poisson, or checking co-boundary conditions. And this is just something that we would be happy for some other people to be involved with and to want to use. So I just want to conclude with several ideas. I think applied geometry is playing an increasingly fundamental role in modern machine learning systems. And there are multiple examples that I've highlighted. I think computational toolkits are really crucial for the development of benchmarks and data sets. And this is something that we do not have in a lot of areas in geometry yet. And this is really, I think, what will drive the advances in the future. So I would encourage everyone that wants to start working in this to think about how they could develop benchmarks and databases. And finally, we have ongoing work that combines our Poisson geometry modules with other geometric statistics tools, GeoMstats, so that they can increase the scope and functionalities of both. And also in the future, we're going to be working with transformers, because this is kind of, I think, a canonical question these days that could be asked. And with that, I just want to thank all of my wonderful collaborators, and also have a shout out to the funding agencies that have supported all my work. And thank you for the invitation. And that's it. Thank you very much.
Thank you very much, Pablo, for this very nice and very interesting talk. So are there any questions? So actually, I have a few questions. So maybe about I mean, there's many things that you touched on, but about the curve shortening flow. I mean, can you do it in, for two-dimensional in three-dimensional in R3?
Yeah, that's a very good question. Let me see if I can go back to that. You can, but it's very computationally expensive. So running, you
I
haven't
guess.
done that yet. I mean, there are several things going on here. Here you have a discretization of the curve into a polygonal curve. So in 2D, you would need to have a set triangulation, and already having one triangulation and how that evolves and how combinatorially that would change throughout this process is hard to figure out computationally. There is interest in doing this for applications to neuroscience and what are called neuromanifolds that parameterize certain aspects of neurons on the brain. So doing this with tori, and that would be easier. There are other difficulties in terms of the geometric analysis of the two-dimensional mean curvature flow in R3, because when you discretize it, there are difficulties that appear in the stability results. So I think it's interesting to consider, and it would be great to do, but I think it's not very easy to generalize. Yeah.
But is the main challenge really is the computational part or more the theoretical? Or
I think there is a theoretical challenge there, which is the showing that the discretization is a good approximation. So that might not seem like theoretical at first, but that's kind of on the numerical analysis theory side, I think. And then, and probably also on the combinatorics of how the triangulation evolves. And then after that, the computational difficulty. In here, Eduardo, who was in the audience, worked very hard on actually getting this to run in parallel so that we could get it to run quicker, because otherwise the runtime of this is very, very long and it would take very long to do. However, there are proposals. I saw a proposal several years ago of using this to understand the growth shape of tumors in 3D. So cancerous growths. So I think there is an interest from different medical fields specifically on being able to do this. But I think that there are some challenges in both theoretical and computational.
I see. Thanks. And with the Poisson geometry, I mean, is there something special about the like Poisson geometry? Can you do it? I mean, this for other? I mean, as long as you have these databases, you could train the network. Sorry, the model. Couldn't you? I mean.
So you mean for?
Why did you choose Poisson geometry? I guess maybe that's the.
Oh well, I guess that's partly because we have this theorem where I'm interested in learning more about Poisson geometry and Poisson manifolds to understand smooth form manifolds. So that's one of my personal motivations. The other motivation really is from the fact that so it's kind of the other way around. In order to prove this theorem, we needed to prove a local model for the Poisson bivector around the Lefschetz singularity. And that was one of the harder aspects that took us a while actually to figure out. But once we did that, and that was Luis Garcia Naranjo who did that, he actually did that using a script for MATLAB that he wrote, or no, for Mathematica, I think. And so really the development of this toolkit it was inspired by the fact that I realized that we could do things computationally from showing this theorem. And then from having showed this, well, because Jose Ruiz is an expert in Poisson geometry, we thought, well, what other things could we implement in code so that we could get machines to work it out for us? Because some of these computations are very hard. Now, this is what led to the development of this symbolic computational toolkit. And yeah, as you say, once you have this, then you could start thinking about generating databases and then doing learning on them and then seeing how much you can get out of it. But for example, one of the projects that I would like to develop in the future is to have a Riemannian geometry symbolic computational kit in Python. which would then do a similar thing to this, but with Riemannian geometry. And this is something that I've been talking about with some of my students and former grad students, because then you could compute, for example, the Ricci curvature or scalar curvature symbolically, or you could compute whether something would be a solution to a geometric flow that you would propose or not. And this could be done computationally. And then you could do learning on whatever happens to these solutions, and do it in a more computationally informed way. So I think that might be a different takeaway. That's a bit more abstract and a bit more panoramic, but yeah. Maybe, hopefully that answered your question, but thanks.
Yes, definitely. Thank you very much, Pablo. Yeah, so maybe are there other questions? So, well, if not, let's thank you, Pablo. Yes. And I would also like to thank the organizers for their kind invitation to host the seminar today, and thank you everyone for attending, and again thank you, Pablo, for this very, very interesting talk. So
thank you, and thanks everyone for coming.